Welcome back, everybody. In this video, we're going to be taking a look at redundant interfaces when it comes to the ASA. And it's actually pretty easy to work with. It takes a little bit of manipulation to get it to work. And the difference between now and before is we're not going to be dealing with two different interfaces. It'll be the same interfaces working together. So if we look at, we go ahead and minimize the server at the moment. If we look at ASA v1, there are two interfaces. You have gig 0/2 and gig 0/3, right? Well, the way that the redundant interface feature works is similar to that of an ether channel when it comes to the grouping, and that's about where it stops. Where ether channels, you load balance over both links. With redundant interfaces, you only use one at a time. If one dies, you bring up the other one and it works, and you can on the fly switch between them. They share the same MAC address, which is the interface redundant MAC address. So what we're going to do is we're going to show how to go through and set this up for VLANs 10 and 20 and 30, because right now gig 2 is for the LAN and gig 3 is for the DMZ. And I haven't tested this out yet, so I'm not sure exactly how it's going to play out, but I'm pretty sure we should be able to, as we create the .1q sub interfaces, or I should say the redundant interfaces and then the sub interfaces attached to those, which does work. I've tested that out. We should be able to apply different security levels, and then the same security level concept should still apply. But once we get beyond that, then we're going to get into IP connectivity and spend quite a bit of time in routing and do some, obviously start up with static routing, then get into OSP, IP, IGRP, RIP, probably a little bit of ISIS and BGP and stuff like that. So really cover the infrastructure, getting it up and running. So without any further ado, let's dive in. So, and I'm going to leave the logging going so you guys can see this as we're going along. And it probably will get a little bit messy. I will logging. Let's go to logging. Is there? Oh, I'll probably just say logging enable. Type in no logging enable. That'll probably disable that. I don't want to do it right now because I'm not trying to show you the back end right now. I just want to keep it pretty crisp to show you what I want you to see. And then when we get into the back and forth style, we should be good. So show interface IP brief. So all of the infrastructure that we set up on the switches is going to stay in place. So the trunking, the encapsulation, the switch port access modes, all that stuff is going to stay in play. What we're going to be focusing on is going to be how we can basically kind of optimize the ASA. So what's a good use case for redundant interfaces? I really don't have one per se, but for the sake of argument, let's assume that, and let me draw this up real quick because it'll make a little bit more sense if I do it that way. Let me do it this way. So in my mind, this is how I would try to make this work, because it makes, to me, in my mind, it makes sense. So you have an ASA sitting here, right? You have, whoa, that's a horrible A. You have an ASA sitting here, and it's doing its thing. And then, so you have internet up this way. That's your internet. Then south of this, you have, or downstream, depending on how you want to look at it, you have two connections coming from two different stacks. So let's say, we'll give two examples. You have a stacking pair, like this, where you stack them connecting like this. So a pair of 3850s, a third pair of 3750s. I don't really care what model switch it is. If it supports stacking, the stacking concept. Or you have the VSS design. Now, I haven't seen documentation on the VSS variation on either the 4500 or the 6500, but then you run VSS. So you would run a link from here to this switch, and then from here to this one. So if either one of these switches died, you'd just be able to fail over. See what I'm saying? So if this switch died right here, you'd be able to, instead of going out, say, port 2, you'd go out port 1. So gig 0/1 would be going out one direction, but because of the on the multi-chassis ether channel on this side here, or the aggregation that you would create here, This side over here would be this switch dies and goes, checks out, doesn't come back. This is where redundant interfaces would make sense to me. Same thing here. If you did something like this, that's the only time. And I know Ether channels are supported on ASA. They're just not supported on the ASA V for whatever reason. But this is how I would go about doing it. And how I would, if I was going to design it, this is how I would go about using it if I was going to use redundant interfaces. However, I'm of the opinion I would have to really demo it and play with it to see if it's going to fail over the way that I need it to. Because if a customer is going to create a port channel here and a port channel here, they're going to expect that both links are going to get used. That's the whole purpose of that, is to load balance over both interfaces at one time, where the redundant interfaces option or redundant interface option, only one interface is active at any point in time. So if this switch died, this switch would take over, this switch would become live, and then this interface would get used right here, instead of this one right here getting used. That's the point here. So that's how I interpret it. I'm happy to debate this, or if someone has experience with this in the comments below, please let me know. I also could see how you could do it for in respect to you're not doing any type of switch aggregation, so no stack-wise, no VSS, no VPC or whatever, and you have individual switches, and but they're uplinked at the same time, but you have one blocked or something along those lines. I'd really have to think through this process because I really haven't ran into a design use case for it before. So I have some ideas or how I could solve it, but I really haven't ever gone through and demoed it out. So that's my take. You can take it for what it is, or you can throw it out the window. Your call. What I am going to go do here is I'm going to type in interface gig0/2.10. I'm going to say no, and .20, same thing, and then 30 on this guy. So show interface IP brief. Perfect. So now the interfaces are up, and that's it. So now we've blown away connectivity. Now what we need to go do is look at the objects of how we're going to set this up. So we're going to type in interface redundant, or in this case here we have redundant. And this is how we're going to say this, redundant. And we're going to say, in this case it's going to be 1, and we create that, and then underneath here we can create whatever IP addressing information we want to do. Pretty straightforward stuff. Now I'm actually going to exit out and type in interface redundant 1.10. Interface redundant 1. Oh, okay. So interface gig0/2 member. Sorry. What is the command again? It is a member interface, I believe is what it's called. Let me see here. Oh, you know what? I bet you okay, I know. Interface redundant 1. And then you type in the member interface. That's right, I forgot about that. Member interface is going to be gig0/2 and gig0/3. Okay? And so that's how that's going to come into play. Now I should be able to say show interface IP brief. The redundant interface 1 is now up, so interface redundant 1 .10. There we go. That's what I was looking for. So VLAN, in this case here is 10. The security level, or I should say the name if, is going to be inside underscore VLAN 10. The IP address is going to be 10.100.10.1/24. And then the security level for this guy is going to be 100. So now I'm just going to pretty much repeat the process that I did in the previous video when it came to the VLANs, and this basically is going to be how it goes. So I'm going to hit the up arrow a few times and do 20. The VLAN is going to be 20. the IP address is going to be 20.1. The security level is going to be 100. And the name if is going to be inside VLAN 20. And show interface IP brief. We see that starting to show up. Show name if. Excellent. So we're going to do the same thing, but because of the fact that we've got the trunking working the way that we need it to, we're going to be able to keep the train rolling here. So we're going to say .30 and VLAN 30. IP address is going to be 172.16.30.1/24. And then the name if is going to be inside or DMZ underscore VLAN 30. Security level is 0. We're going to set security level is going to be 50. And show interface IP brief. Ta-da! It's all working. So that's what we've done so far. So now if we do a show run pipe include same, we have the same security permit interface and all that other stuff. We do a show name or a show ARP. We're going to start communicating now. So we're going to go to test 9. We're going to come in here and do a ping to 10.100.10.1. If I could spell, that would be awesome. And then test 10. 10.100.10.10 or .1. That one works. This guy will be the same thing. Ping 10.100.20.1. And then we're going to go over to test 12 and we're going to say ping 172.16.30.1. Excellent. So go back over to the ASA, do a show ARP again, and now we have the ARP entries showing up. Everything's looking good. And so now if we go exit out here, type in logging enabled, and I go to test 9, and I do a telnet to 172.16.30.12. I am able to log in, and all of that good stuff. We see the connection form up, and everything looks good there. But if we go to test 12, and we try to ping to 10.100.10.9, we go back over here to the ASA, we see the denials. Now, you might say, okay, well, how is that helpful with the redundant interface? Well, how it's helpful here is this. It's to show interface redundant 1 and summary. So if we come in here, we look at this, we see that the MAC address that's been allocated, and the speed is gigabit, the flow duplex is full, all that type of stuff. We see that gig 0/2 is the active one. Gig 0/3 is inactive. But the idea here is if something was to fail, that it should be able to fail over. Then we can type in interface, or is it redundant interface redundant 1 active member, and we say gigabit 0/3. So now we've made that. So now we've made it from now if we look over here to this, now we see that gig 0/3 is the active one, 2 is not. But if we go back to test 9, we're still connected to switch test 12. And if we look back here, we do a show con long, we never dropped our connection. Why did we never drop our connection? Because the MAC address never changed and the connection never actually dropped. So that's where this comes into play. This is why having the redundancy in here, it's not a bad idea. I mean, is it quite as expansive as the Ether channel? No. Does it give me the ability to load balance? No. But it gives you that peace of mind that if you have a failure on one part of your network, that the ASA will automatically be able to detect that problem and remediate it. Now, if we look at the switch here, and I'm not going to get into a long drawn out, spanning tree reconvergence and all that type of stuff. Understand that still takes a place in it. But if we show MAC address table dynamic, we're going to see what ports we're talking about. So here we have gig 00 and gig 01. So we know that there's going to be connectivity for specific VLANs. So if we know which MAC address that guy is located on, and we know, give me 1 second here to pull that information up. We know this MAC address right here, that's 003 on switch 1. If we do this, we know that 5000 or 0004, 0003 is on gig 0/1. Now, what's interesting about this is I bet you if we switch back and we do this to 2, right? And we go back to the switch 1, and we hit the up arrow, three will be on gig 00. So the switch automatically knows which port to flip it out of, and that happened that quickly. However, the reason why I was able to do that, spanning tree, show spanning tree, is because we're running rapid spanning tree. So rapid spanning tree protocol is able to reconverge super fast to figure out, okay, why is it taking so long for that to happen, and what's the deal? So that is why it happens as quickly as it does. Now, here's the thing. When we're talking about a situation like this, one key thing you have to remember is there is no MAC address flush and flood. The MAC address, like an HSRP group or VRRP group or GLBP group, isn't changing. So just because it looks like the interfaces are changing on the switch, which they are, you can clearly tell the port switched from 0/1 to 0/0 depending on which redundant interface was active. So because it's swapped based off of the active interface in the connection, if you were to configure this into a port channel, so let's attempt that real quick. So we'll type in interface range gig 0/0 through 1. We'll just go ahead and we'll shut it down, so we don't have any problems with negotiation. We'll type in channel group 1 mode is on. So we're not going to do any negotiation. We'll type in interface port channel 1, and we'll do a do show run interface PO1. It should automatically grab. Okay, so it didn't grab the config. We'll type in switch port trunk and cat.1q. Switch port mode is trunk, and we'll type in no shut. Interface range gig 0/0 through 1, no shut. Let's bring those ports back up. So the port channel is up. Do show interface trunk. We should see the port channel is there. Now we have to wait a moment for spanning tree to go into forwarding mode. And that should take a couple of seconds. Now, considering I shut the interfaces down, there it goes. So now, if I do a show spanning tree for VLAN 10, we're going to see that port channel 1 connects up to that upstream connection, right? Now, if I go back to the ASA and I say, okay, well, if I do show port this, we're going to see that 3 is still there. If I go back to 9 and I hit I can't connect to that, so I Control-Shift-6X and I break out of that, and it tries to connect. It's going to have to resynchronize. All that stuff has to be, the flood and learn has to take effect because I blew those. So let's do show IP interface brief. Let's go ahead and ping 10.100.10.1. Show interface IP brief. Okay, so that should be all good. Show ARP. So let me go ahead and, so I'm getting a rate drop, which is interesting. So there may be a problem with having the port channel created on the switch with a redundant interface connecting up northbound. Now the idea was to optimize it to where you wouldn't have the interface swapping, but that may not be supported here in software. But so in this particular case, I'm getting an interface drop rate 1 exceeded. Current burst rate is set. I'm not sure. But what I'm going to do is, what I wanted to show you was a redundant aspect of it to see if it could flip back and forth, and that did work. So, not sure what that is. It's a lot of drops if it's, what is that, 7 million drops per second? That's a lot. So, as far as I'm concerned, that's pretty much. Let me go back to the ASA and try to ping outbound. Let me ping 10.1, 100.10.9. I'm getting question marks. Okay, so basically, let me do this. Let me go to switch 1, and let me do. Oh, there were some issues on the switch side. That's the only drawback to show MAC address table dynamic. So let's try this one more time. On this PC side, okay, there we go. Okay, so all right. So basically, what issue you will see every now and then with Eve, with these devices running in there, is whenever you have a problem with spanning, anytime spanning tree needs to reconverge, it seems like there's an overload of what's going on. So let's just go up here and ping there. That should work now too. After a moment, hopefully. You never know. Okay, that worked. Not sure why 10's not working. And then 12 should work as well. But switch 1. It should be working here momentarily. ASA 1 should be able to ping, and he can. That worked for sure. If I do 10, that one looks like it's going to be failing. It's sending it but not receiving it. So Control C on that one. Q. Let's see here. Let's do a show ARP. So I just wanted to show you that. I'm actually going to revert the port channel back in between videos, and we're going to remove the redundant interface, and then we're going to focus on there's some MTU stuff that there's also as well, but beyond that, not a whole lot to really focus on when it comes to that. If you need a higher than 1500 byte MTU, then you can focus on that later on. You can bump that up. But beyond that, there's really not a whole lot more to it. The next set of topics we're going to be diving into is IP connectivity, which is going to be things like DHCP, of doing some routing, and then a static routing, RIP, EIGRP, OSPF, BGP, etc. So I am curious to see if test 10 is back yet. Let me show IP interface brief. That perplexes me that it's not back yet. That's okay though, because I'm going to go ahead and delete and get rid of the redundant interface, and I'm going to get rid of I'm going to go back to sub interfaces in between videos. I'll rebuild that, and then you guys will be able to go through, and we'll pick up from there, and we'll dive into like doing DHCP on the LAN, and then doing some basic routing and stuff like that. Doing DHCP, we'll actually do DHCP, and we'll then do a static route, and then I will probably, and I'll do DNS, actually, I'll probably do static route, then enable dynamic routing, and then I'll do DHCP, because eventually server 2 will eventually get internet access, and once we have internet access and stuff like that, then we'll be able to test a lot of this other capabilities, because then we'll dive into access control and then NAT from there. So I'm sorry a little bit off the cuff, but you know, it's okay. Until next time, guys, take it easy.